And while I am on record, I should keep the record straight. Greg threw me under the bus twice. I saw his recording of the final exam, and he keeps not mentioning that I said you can have them do all 4 in grade 3. But whatever. Anyways,
it's too late, Paul. It's too late.
It's too late. It's too late. But I am responsible for the long test. Yes. Okay. Okay. So let's get started. But I guess before I do, did you guys have any questions on anything before I start?
I have a question, Paul, about the short answer. So I emailed Greg about it, but is the short answer, I mean, not short answer, I'm sorry, everyone, short paper for the natural experiment. On the syllabus, it said that it's due like week 9, beginning of class. And I was kind of confused by Greg's announcement that it was due as part of like the short answers for this week.
Yeah, that also threw me off. I don't know. I would suggest emailing him and getting a clarification, and I'm sure he'll send out an announcement.
Okay, I emailed him, so I will wait until he responds then.
Yeah, and it shouldn't be like too much of a lift. I think in his mind and also in my mind, it should not take you longer than like problem set. Not the short ones, but like the average problem set. But who knows? But I imagine he'll give you an extension if you need more time. If you get stuck on figuring out how to like construct a natural experiment, then you can reach out to either of us. I am not exactly sure what Greg's expectations are in terms of like how formal. By formal, I mean like mathematical equations that you need to present. It may not. So that's also something that you can ask him about. I don't know the answers to that. And I think also Greg will be the one to grade and give you feedback on that piece too. So sorry. Yeah.
No worries, thank you.
Yeah. Also so this is the second to last Stata problem set. The very last one is not using Stata, but using a different program, which is pretty easy to use. It's just doing a power analysis. You just follow like steps, and that's shouldn't be hard. This problem set shouldn't also take you too much time either. There's nothing like super new. The next problem set, which is probably going to be, I think it's 2 weeks from now. So there's no problem set next week. And then there's a problem set on week 9. That one is going to be new and kind of hard-ish, but not as time consuming or intensive as the earlier ones, or shouldn't be. But we will see. Okay, I'll get started. Today we're going to talk about how to collapse the data, which is important if you want to try and create bin scatters, or if you just are working with different kinds of data and you need to get your data to a particular level. So for example, if you have student level data, but you want school level statistics, then you might want to collapse your data to the school level. Or if you, let's say, have for every row, 1 person at one time, and you have like 10 observations per that 1 person, then you might want to collapse it to the person level and try to get to, do something with that. Then we're going to cover spline analysis, which you have seen before. And then if there's time, some extras, but I don't know if there will be too much time.
Sorry, Paul, not to interrupt you, but I just wanted to clarify. So you said that next week there isn't a problem set due. Is this so that we can prepare for our papers that we'll be turning in on week 9?
So that was my understanding, but I am also confused, so I'm not sure.
Okay.
But I'm pretty sure we don't have a problem set next week, but I'll confirm with Greg.
Thank you. I appreciate that.
Yeah. Okay. Okay, here we go. So I'm gonna cover this part last because it's something that you should know, like the difference between LPM and logits. And something that I ask you to do for this week's problem set is how do you know if LPM is giving you something similar? And how can you sort of say like, all right, I'm gonna just use LPM for now and add logits later, like that you're not being misled. Right? I've kind of covered it in previous weeks, but I'll come back to this if we have time at the end. But for now, I'll skip it. We're going to go through some basics of Stata graphing. And something that's kind of useful is this thing called palettes. It's a user-created package, so it's not official to Stata. But it gives you some like nice information. If you want to install it, you can do SSE install palettes. And then you have to install like 2 more things. But again, for something like this, if you're working from the UCI server, I forget the name, then you have to put in that line before you install like stab. Whatever it is that sort of changes the directory of your ADO files or these other packages that you're installing so that it will install there. But once you do install it, you can look at the help menu, which gives you some commands that you could be using and some details about what it has. And you can just run stuff like color palette. I don't know why there's a 9 here. It's going to bring up for you a figure soon once it runs. And there are like many color palettes. They're like labeled S1, S2, or like economist. If you wanted to pick a particular color, so you can label your graphs, or you can like color your lines or scatter or whatever it is, you can use this. You can also just Google like Stata palettes or color palettes, and this will come up. It's just a nice thing to have like embedded into your Stata in case, you know, like you forgot and you want to look it up, but you don't want to Google it, or maybe you don't have internet access because you're like on the road or on the plane, whatever, right? Like you can look up colors here. There's also a line palette. And like if you want a solid line, which is the default, you can say like, for the line, I want it to be solid, or a dash dot, or long dash, short dash, whatever dash, right? Then you can add, you can change the dots. So it's not just a circle, but it's like a plus sign or a small circle, a hollow circle, a diamond, a square, whatever. And you can look up all of these things online also, but this is just one convenient way of getting it. So if you can't install palettes, don't worry. It's not essential. Okay. So a motivating example for like why we want this bin scatter. We created an ugly scatter before a couple of weeks ago in lab. This is when we were looking at the relationship between science scores and SES and interacting it with whether a student is in public school or private school or whatever. And it looked like this. It will, sorry. Where did it go? There's a mistake there. And this was not super informative. It's hard to see what this pattern of the scatter are. There are just too many to see. And we said, we're going to call this an ugly graph, but just leave it alone for now. And what we've talked about is we want to try and bin the graph. And what that means is instead of having like a continuous x-axis, we want to create bins so that we can get the average y value for every bin. And I'll cover these in detail, but for now, just trust me, this is creating these bins for SES. And this is a histogram of the bins, which should look like the histogram of SES. And we're going to collapse the data, and I'll cover these in detail, which gives us something like a much smaller data set, right? You see there are only 70 rows instead of like 20,000. That will allow us to graph something like this. Now, for every dot, what you're seeing is not an individual, but the average Y, so the average 8th grade science test score for the person in this bin, for the person in this bin, that bin, and so forth. And now the pattern is a little bit easier to see. You can kind of see that there is this upward trend. It's a little nonlinear, a linear-ish looking scatter pattern for non-public students or students in private school. And you see this like noisy scatter where there's not a clear pattern. And this is why it's important to look at the histogram. You have very little data, right? At the very low SES and at the very high SES. And so it's hard to trust whether this line or this scatter is representative. You just don't have a very good sample there. So it's hard to project what the relationship should be. Or here, although maybe there's some kind of relationship here too, but it's again very hard to tell. And now we say like, okay, so the histogram tells us most of the data are above -2 Z SES, standardized SES. So we can try just limiting it to that range. So anything above -2. And we'll change the colors a little bit. So it's not just orange and like hollow circle. And then we're gonna fit like multiple lines. So here we had like, what did I do here? Right, like we feel like this here is pretty noisy. So let's put a separate line. We'll add another line here, make it a little bit better. It fits the scatter a little bit better than before. And I don't know why I didn't limit it. I don't know why I showed this. I think what I wanted to show was just things above -2. But you don't always want to do that. Just because you have an outlier doesn't mean they're not important. They're like real people. It just means that you just don't have a lot of confidence. And this zero slope or near zero slope could be representing a lot of noise, or it could be representing like a non-relationship, but you wouldn't be able to like come to one conclusion or the other. Okay. And let's now sort of simplify it and take a closer look at just the public school kids and break them out into like 3 chunks. So kids below -2, between -2 and maybe 0. So like very low SES, then maybe like low SES and then higher SES. And you have a curve that seems to fit better. And this is the kind of spline function that Greg uses on the income to schooling relationship, where you see a much sharper slope for low-income families in the relationship between income and years of schooling, and a much shallower slope for families who had much higher income. And this is just sort of to get like a quick preview as to what your data looks like and how you might want to fit a spline function, or where you might decide the split should be. Okay, so this is just sort of like a quick preview into like what we will try to digest in code and how you can arrive at this figure on your own and like understanding what's going on. So we're gonna go back to the student level data and like repeat these steps. So I've now reloaded our lab file. This is line 119. And recall that for all of these figures, I've like limited it to a particular sample. Like all of these scatters were for if they were part of our sample indicator in lab 4. Okay. So I'm gonna now, just to make things easier, right? Instead of having to create an if statement after every command, I'm just gonna drop the ones that are not in our sample, or keep the records that are only in our sample. So we lose like 13,000 observations. Okay. And now, how do we create our bins? Up on the top here, this was the code that created our bin. Like generate this thing. If it's like my 0.2 times floor of the Z SES divided by 0.2, but like what is that doing? And that's what I'll show you. Floor is useful, And you can look up the documentation here. It's not like super descriptive. But let's say we have a number like 1.98 and we apply floor to it. Right? It gives us 1. If I apply the floor to 1.91, it gives me 1. 1.11, it gives me 1. And the pattern is that it's basically just rounding down to the integer. Right? It's not rounding up, it's purely rounding down. And it turns out that you can use a combination of floors, dividing by the bin size and multiplying by the bin size to create your bin labels. And it's kind of weird, right? Like this is the full code here. If you think about it, it's just if you multiply something by 0.2 and you divide something by 0.2, it cancels, right? So let's say we take the first part of this, which is the inside of the parentheses. We'll take ZSES, divide it by 0.2. And 0.2 is sort of the size of the bin, right? We can decide it will be 0.1, and that's totally fine. It'll just mean that the bin on the x-axis will be smaller. We can make it 0.5, and it'll just make the bins larger. But if we take this first step, and I'll browse the data so you can see it. Right. Over here is ZSES. And let's sort it. So you have the smallest SES here. And on the very bottom, you have the largest SES. I don't know how to make this bigger. Okay. And so if I apply step 1 and say divide by 0.2, it's going to give me a very big number. It'll multiply by 5, right? Dividing by 0.2. And of course, if I apply this multiplier here, right, and call it step 2, it's just going to bring me back to 3.41. I'm just doing something right before I do this, which is apply floor. So I'm going to apply floor to step 1, this thing that's been divided by 0.2. And that gives me the integer value, right, of this decimal. Then if I apply the outside step of multiplying by 0.2, it'll give me the bins, right? And so now 3.41 is inside bin 3.4. 3.34 is inside bin 3.2. Same thing here, because it's a negative number, right? The floor of negative 5.9 is negative 6. And then it goes up in increments of 2. And you can do this all in one step. I just broke it out so that you know what the code was doing. And we can tab this to sort of see. Tab ZSES bin. And you can tell like it is just moving in 0.2 increments, except when there's no data there. So like there's no data for the 5.8 bin because there's nobody in the range of negative 5.8 to negative 5.6. So the creating of these floors is pretty simple. It's just one line. This is hard. It's like it feels uncomfortable because it's not a natural way of thinking about the sort of the numbers. But this is how you get to these bin sizes. And when you create the bins, it's generally a good idea to look at the bins like by tabbing it to making sure like you made it right. Creating histograms to make sure that your raw histogram and your bin histogram looks more or less pretty similar in terms of its distribution size, but you can sort of see where it's changing a little bit. And it's always a good idea to know like where most of your data are, which you can tell from the raw variables, but from your bin variables too. Okay.
Paul, I have a question.
Yeah.
So if we go back up to Gen step, is step 3 supposed to be the floor of step 2?
No, so step 2 is like redundant. I was just showing you that if you divide something by a number and multiply by that number, it cancels.
Oh, okay.
So you don't. Sorry, maybe I shouldn't have called it a step. I was just trying to get you to see that it's giving you back the same number, right? But it's doing something in between called floor.
Gotcha. Thank you.
Yeah. Okay. So now that you have these bins, you want to try and collapse the data. But there are multiple ways of creating bins, but I want you to understand how collapsing works. It's handy for a lot of things. Like recall that if you run like the scribe, it's getting long. Okay. You know that there are, okay, well, there used to be 21,000, but after we've like dropped the people who are not in our sample, you have like 7,000 rows. And if you run codebook for your bins, you know that there are 43 unique values. So that what you want now are like basically 43 bins. I don't know why I wrote 46 here. So something went wrong. And it's a question of how do you get to those 46 bins? So you have one row for every bin. And you can look at this help documentation later. Well, actually, maybe just now. It will allow you, right, to sort of take each bin and create the mean value, the median value, the first percentile, the standard deviation, the sum of all of those values. You're basically just shrinking it down, right? But once you collapse the data, you can't just hit like Control Z to undo the collapse. It's like permanent. And so, and of course, if you don't like what happened, you can just go back up to the top of your do file, run everything. But it's a little bit convenient to just save the file before you collapse it. For like this kind of demonstration, it's not necessary. So I've saved the file. Maybe I've already done. Okay. And for now, we're just gonna focus on public school kids, just to make things easy. And if we do, I don't know why I'm getting like different numbers than what I wrote down last night, but it'll tell you the number of bins that you should get. And I guess it's 42. So if you collapse the data, you specify what level the data will be after the collapse, which means what will each row represent. And here it'll be ZSES bin, which is a range from -6 all the way to like 4 something in increments of 0.2. And inside, for every row, we want to now take the mean value of the outcome variable. And if I say take the mean value of the public, it doesn't matter because everybody gets a 1, right? A mean value of lots of 1s is just 1. And so if I collapse the data now looks like this. All of your variables are gone except for the ones you specified. The level that you wanted, the ZSES bin, the variables that you wanted to save, the mean values of ZSES, and the mean values of the public. And this is not important. So this here, this number of -0.192, sorry, I know it's a little small. This, I know how to make it bigger. Here, let's list in one. Okay. This number, right, this represents the average science score for the students who are in this bin of -6, which is between like -6 to -5.8. And this now represents the average science score for the students in this bin, -5.6. Okay, and you only now have 42, which is consistent with the codebook saying there were 42 unique values. You can also browse the data to confirm. And it should look pretty easy to handle. And now what you have is you basically have these two variables that become the part of your graph. The bin becomes your x-axis or your horizontal axis. Z sin 7, which is now the mean value of Z sin 7, is going to be your y-axis. So you can just do a scatter. Right? And this is what we saw before, minus all the graph formatting. And we'll just add some stuff here. And I'll walk you through this here. I want to scatter, right? Based on this, I want a line for before -2, from -2 to 0, and from 0 to the rest. And so here I've asked for 3 scatters. Same thing. It's the same code as that you saw above. Scatter the y on the x for public school students. This is everyone, and so you don't need this piece. if SES is less than -2. And for M color, M, I don't know why it's called M, but this is the color of your dot. I'm gonna say G3, which is grayscale 3. And let's make it an M symbol, which means for the same M, the same dot, let's make it a circle that's hollowed out. Let's do the same thing for a different range, the next range, give them different colors and symbols that's a little bit different. Yeah. And then I'm gonna fit a line, which is lfit, right? Same thing, lfit the outcome or the y on the x for the same ranges and give them different line colors and line patterns. And the legend, this is sort of like weird syntax. This one corresponds to the first thing you write. So the first, like a scatter or figure or whatever, right? Stata understands the legend by numbering the sequence of graphings that you, like graphing objects that you have. So this is number 1, this is number 2, 3, 4, 5, 6. But we only really need to label 3 things. This is why we only have 1, 2, 3. And I've labeled them public, very low SES, public, lower SES, public, higher SES. And I wrote a note here so that you know what low SES means or what very low SES means. And this is essentially the same graph you saw before. So just very quickly, right? You saw, you run a scatter because you want to take a quick look at the relationship between X and Y. Not very helpful, so you want to create bins. So you create your bins using the floor function. Then you use collapse to collapse your data to just a limited number of observations, 1 row per bin. Then you run the same scatter plot, treating all of them like like an axis. This is the x-axis, this is the y-axis, and so forth. And we covered like RD in class during lecture a lot. And the bin scatters are essential to figuring out if you have an RD design, right? So if you imagine you have like a line here, and this was the threshold for the discontinuity, you would want to run a bin scatter to make sure that there's this like kind of a line here, that kind of a line here, and that there's a gap in the intercept. So the same kind of functions in the code that you're seeing here would get applied for a regression discontinuity analysis. But it's very hard to find an RD example. And I'm not aware of any RD designs within the EPELS-K, which is why we can't do an RD practice. And instead, what we're going to try to do is something similar, which is a spline analysis. Yeah. And I showed you the simplest collapse, the simplest way to collapse the data. So let's go back to our student level data. And recall that before we were trying to plot the scatter for public school kids and private school kids. That means for each bin, right? Each bin, we want public school kids and private school kids. So right, so that 1 bin is actually now 2 bins. We need 1 bin for 1 group, another bin for the other group for every one of the SES bins. How do you do that? It's not hard. You just your level is now no longer SES bin. It is SES bin with public status. So if you collapse this, what happens? We can browse this, right? You don't have a 1, 0 for every bin, right? You don't have any kids who go to private school that are in the lowest SES bin. So let's look here, for example. And I'll print this out so it's a little bit bigger. Right. This is the -2.6 bin. These are the kids who are not in public school. These are the kids who are in public school. This is their outcome score for the kids who are in private school. The outcome score or the science score for the kids who are in public school. So not hard, just adding 1 more level. Before you saw like 40 something rows, now you see like 70 rows because you have more bins now, right? For your private school kids. Okay. And this is the same graph we saw before. Now we can graph it separately, or a separate scatter and a separate line for private school kids, and a separate scatter and a separate line for public school kids. And let's go back to our student level data again.
Sorry, can I ask
Yeah, yeah.
something? Yeah. So it shows that like for our like -6 SES pin, there isn't any student who goes to a private school.
Yeah, yeah.
Okay.
Yeah. Okay. So we'll go back to our student level data, and you can take whatever statistic that you want, right? If you recall, if you go to the collapse help document, you can choose to take the median, the mean, so depending on what you're doing, or the standard deviation, and you can save as many variables as you want. Now, one thing I want to try and get you to think about, and this becomes important if you ever do an RD analysis, is that sometimes you want to know how many people are in each bin. And of course, at the student level data, you already have this information, right? If you just tabulate your bin variable, you know how many people are in each bin. But if you want to now use collapse, but you want to hold on to that information so that at the end of this process, right, you have the bin size, the average outcome, but also how many people are in each bin. How do you do that? How can you get that statistic? And just sort of like thinking through, tell me what would help you get that information.
Maybe sum divided by average. Do we get the sum over each bin?
Okay, so let's do something like that here first. Let's first limit our sample like we have done before. And what are you thinking?
So can we get the sum of the data by their bin? Something like that, yeah.
Yeah,
And
so
then divided by the mean of it.
so something like this.
Yeah, so if we divide that by the mean of each bin,
The mean
then
of
we
each
get
bin. Okay,
the
so
mean of like science, for example, for
okay.
each bin. Then
So this will give me the mean of this variable. This will give me the sum of this variable. And I'm gonna make this SES mean. I'll say SES n. This is I'm gonna take the mean of ZSES bin, like you're saying, put it into a variable called SES mean. I'll call it ZSES mean to be consistent. And then I'm gonna take the sum of SES bin and then make it ZSES n. Is this what you're saying?
yeah, so then if we divide their sum,
Okay.
no, this is not what I meant.
This is not what you meant.
Yeah, I wanted the sum of Z science.
Z science. You want the sum of Z science.
Yeah.
Okay. And science. Okay.
Yeah, so now if you just like divide sum of Z science by each mean, and then divide that by their average, then we get how many people are there in.
So I'm gonna collapse this. This is what you want, right?
Probably.
Okay. So we'll go there, right? ZSES bin is not. Oh, sorry, I have to create the bin first. Where's the bin? Creating function. Okay. ZSES bin is already defined. It's already in here. But maybe to continue with what you were saying. Sorry. Oh, it's already here. I don't have to regenerate this. Why is it saying it's not found? Okay. I'm not sure why it's saying it's not found, but let's. Sorry, that's a weird quirk. But instead of troubleshooting it live, it's not. I'll give you an easier way. There's a much easier way, which I'm sure you assume. There's a much easier way. You can say like you can generate a variable, call it count, and everybody gets a 1. Right? Everybody gets a 1. And then when I take the mean, I can just take the sum of the count. Right? And it will be there. Because all that it did was everybody had a count of 1, and I just take the sum of the counts. And it'll give me how many people are in each bin. So it takes times getting used to. It would have been nice if I could show you what Amin was thinking, but I don't know what happened with the code there. But I don't want to take up your time troubleshooting. But this is sort of a way to like get the statistics that you want. And it is sort of useful, right? Baiting the scatter, it's useful for getting an idea for like where should the split be for your spline function if you ever wanted to use a spline. And in this section below, I'm going to cover how do you run a spline analysis. But before I move on, right, I like quickly went over like a new data command and manipulation, graphing. Are there any questions there on what we covered before we now move to trying to run a spline analysis? Okay. No questions, I presume. Okay. So we're going to go back to our student level data again. And for simplicity, for the purposes of this lab, we're going to just focus on public school kids. And we'll create 3 segments. An indicator that tells me you're in a very low SES, you're in low SES, you're in higher SES. Right? This is the breakdown that we used before. Okay. And I've created the variable is 1, 0, but I want to make sure I'm fixing all the missings. So I'm going to replace all the missings and then take a quick summary to see that for these 3 indicators, right, the min and the max, they don't overlap. They are in fact distinct, right? Just ways of doing quality control. But you didn't have to worry about that because there was no missing data, I suppose, with SES here in our subsample. Okay. And recall that the basic regression looks like this. You're regressing the outcome on SES. But how do you now add the spline function? And you can go back and think about what we created. How do you now, you have an indicator for who's in which group. You have 3 groups. And then you have a regression. But now, how do you add the spline function? And sort of the hint is like, what does each line of the spline function require? How are the lines different? When you run a regression, you have 1 line. When you have a spline function like this one, you have 3 lines. So what do you need?
The slopes are different?
Yeah, the slopes are different. What else is different?
So we just have to run 1 regression for each part, right?
Well, if you run a regression for each part, you can get the information here, but I guess, and that could work. You could do that, but traditionally spline functions are not run separately. They're run in one equation and in one regression. But you
So
have the
I
right
think,
idea.
yeah, we need to add interactions, right?
Yeah.
Because like, yeah, you just at the
Different.
beginning of the lab, you said we were gonna review
Yeah.
functions. So yeah.
That's right. And so, but before we run interactions, a quick question. People said you need different slopes. What else do you need that's different for the different lines?
Intercept.
Right, you need a different intercept. And as you know from interactions, the interaction term gives you different slopes. The dummy variable gives you a different intercept, right? And so let's now add the interaction term. Let's do something like this. For every variable, our indicator of being very low, low, and higher, I'm going to generate this thing called ZSES. X interacted with this variable by taking the product of ZSES and this dummy variable. Right? This is the thing you're interacting. Right? This is different from another interaction where you are interacting two different variables. But here you're interacting the same variable, one that's continuous and one that is a dummy. Okay? And you don't want to add, right now you have 3 dummies and 3 interactions. And you don't want to add all 6 because you need to omit one group. Okay? So we're going to omit the very low group. And this will be our like reference category. And run this. And it gives you something like that. And this is what we're going to try and spend time on, like interpreting. And it's not the easiest thing to interpret the first time around, but once you sort of see it, it should be fairly easy. Can you tell me what each of these things mean? Or let's maybe we'll just start here. Okay. What does this mean? The 0.580. Okay, let's start with something simpler. What does this mean here? ZSES. Like this is remember the basic regression was this one, right, where we just regress the outcome on the predictor. And it's not the same, right? It's not the same. So you don't interpret it in the exact same way, although they're very similar. So how do you interpret this?
So this is the linear relationship between ZSCS and Z-science for very low group.
Yeah. Because you would have to assume zeros here. Someone who is 0 in low SES and a higher SES is someone that has very low SES and is 0 here too, right? These just cancel out because you have the 0, they disappear. So then what is this?
So this is the difference it makes for low SES compared to very low. So like for each increase in each one standard deviation increase, there will be like 0.58 more increase in Z science for low SES group compared to very low SES group.
Yeah, that's right. That's right. And so how do you get the slope? And let's do this. One way to check to see if you ran this right is to just look at the y-hats, right? This regression is going to give you the predicted Z science value for every individual, right? And let's predict y-hats. And let's scatter that y-hats on ZSES. Wait, that's the wrong regression, right? And I know it looks a little bit different because the y scale is different, but you can kind of tell, like, all right, we have 3 different slopes, so the spline is kind of working. Okay. So what is this slope here? What's the magnitude of that slope?
Would it be the ZSCS with the ZSCS low? Because it's super steep.
I mean, these two things?
I'm talking about the ZSCS X ZSCS low, because it has an incredibly steep slope. So wouldn't that be the 0.58?
Yeah, so are you saying that this slope is 0.58?
Yes.
It's close, but not exactly.
This is the sum of 0.58 and 2.7.
Right.
These two.
So it'll be this plus this. So Scorepad, do you see why it would be the sum of these two things and not just this alone?
Refresh my brain here. Why would it be the sum of these two?
Yeah, so if we write out the equation, it's going to be, I'm trying to make this bigger. Oh, maybe I can write it out here. Okay, if we write out the equation, it's going to be science, and I'll just use a shorthand. All right, science is going to equal to ZSES, ZSES low, ZSES higher.
Oh,
right.
okay. So okay.
Okay, so you see what's happening?
Yeah. It's
Right.
put it because you're looking at science, so you need to look at all of them together.
What do you mean?
Well, like you're looking at the ZSCS low plus the ZSCS. Well, ZSCS when compared or interacting with ZSCS low and then ZSCS with it by itself, right?
Right. So if I for this person on this sharp slope, we know that of our 3 groups, very low, low, and higher,
Mm-hmm.
they are in the low group. So they get a 1 here, right? There's a beta in front. I forgot to write the betas, right? So they're going to get a 1 here. They're going to get a 0.
Mm-hmm.
And then they're going to get a, well, this is 1, right?
Mm-hmm. Mm-hmm.
But you know, they hold on to this. This is 0.
This is
right?
0. Yep.
So this basically goes away, right? And this is just whatever that beta was. I should have numbered that, right?
Right.
And then this is 1. And so you have the sum of this beta with that beta.
This seeing it this way makes a lot more sense.
Yeah, okay, cool. And so the sum of this slope, or to get this slope, you would take ZSES and you would add in ZSES higher. And you can tell it's not as sharp. And this is why what you add to ZSES is not as steep. Right?
Okay, this makes a lot. Okay, thank you.
Yeah.
Writing it like that there really helped out.
Yeah, okay. And you can tell, like, they have different, like, intercepts too, but the constant is hard to interpret. The constant is hard to interpret, and the dummies are hard to interpret. And maybe you can figure out why. Like, up here, who has, of these 3 groups, who has the smallest intercept when you think about graphing? It's probably this group. I'm not entirely sure. But the constants, but the way, like, like when you think about a line, you think about an intercept and then a line that moves. But mathematically, intercept is when x equals 0. This is the intercept for all 3 lines when x is equal to 0. So you have to project this line to 0, right? And that's what makes this hard to read, because the x-axis is not going from 0 to whatever. It's going from a negative number to a positive number. So if you look at ZSES low, right? And this is the thing that gives you a separate intercept for people who are in low SES. It's 0.85, and the constant is 0.724, which is the intercept of the person who's in the lowest SES category. For the person who's in the higher SES category, their intercept, the coefficient here is 0.02, which is lower than 0.08, right? This starts much higher than this. But the coefficient is smaller because by intercept, right? The way mathematically you understand intercept is not where the line begins. It's where the line hits 0. And that's why it's so weird. And that's why for a spline function that uses an x variable that goes from a negative number to a positive number, it's very hard to interpret this naturally, interpret the intercepts naturally. But I mean, oftentimes you don't really care so much about the intercept and you care much more about the slope and the difference in the slope. So this is confusing. That's okay. I can cover it in more detail, but that's sort of the crux of adding running a spline function. You're interacting the variable to itself, except one time it's a continuous variable, the other term is a dummy variable. And that takes getting some used to. And you might have wondered, like, this graph doesn't look like what you saw here. Right? It just seems so sharp, and it's just the difference in the scale. So if we collapse this, where what I'll be scattering, same thing, I'll just scatter y hat and ZSES, y hat and ZSES. It is now plotting. I don't think I collapsed this. It's now just plotting the same y hat, just the average y hat, and drawing a line through it. But anyways, okay. So that's the spline function, and I'll stop to get questions on the spline, and then if there's, and I think since there's time, I'll go over the logits for anyone who's maybe not sure. But any questions on the spline? Are you feeling okay, comfortable?
So is there like, besides like seeing the dots, is there any difference between like graphing y hat or just like graphing the line on its own? So like this is the line, right?
Oh yeah, like if you did this instead. Is that what you mean?
No, it just yeah.
Yeah?
Yeah.
Oh yeah. Lines are off. Something is happening here. Yeah, so something's happening here from the estimate that's different from the raw scatter. Okay, so maybe it was steeper than it should have been. And that's a little odd. But
yeah, but it should have been the same, right?
Yeah, it should have been the same. So I probably made a coding error somewhere. And I'll figure out the coding error and then tell you where I messed up on the code. But this mistake aside, the functions of a spline, this is still the way to run it. And I don't know what happened here. So I'm trying to figure out whether this is the nature of binning or if it's a coding error, but thanks for spotting that. I will fix that and give you an update.
So is the regression limited to public?
Right now, maybe that's, yeah, but right now, yeah, but that should not matter. This one
Oh.
is this entire thing is limited to public sample.
Yeah, should have been the same then.
Yeah, it should have been the same. So I'll look into why this is not the same. I'll fix this.
Yeah, thanks.
Okay. Other questions on this line?
For the size of the bins, do we usually use 0.2, or would that be something we decide on based on the data?
Yeah, so you do that based on the data. So for example, let's say you wanted to run an RD and you wanted to see if, say, being in a different birth cohort mattered. And maybe, let's say, like anyone born in like April of 2000 didn't get treatment. Anyone born May of 2000 got treatment. Then you would want every bin to be 1 month, in which case it wouldn't be 0.2. The choice of 0.2 is kind of arbitrary. And in an RD analysis, you would want to make sure that the bin size doesn't sort of change your final outcome. So some people, you can trick people into thinking there is a discontinuity if you use a larger bin, because then there's a higher chance that there's a discontinuity, right? So something like 0.5, as opposed to something like 0.1. It's much harder to see a discontinuity when bin sizes are smaller. And so the presentation, and so you want to check that doesn't matter what your bin sizes are, even if it's very small, that you still have a discontinuity, but you just present something that's more readable or understandable for people. And for now, I just arbitrarily chose 0.2, but we could have done 0.1.
Yeah, I think the smaller your bin size is, the closer it would get to the original continuous variable.
Yeah.
And like it depends on what you want to be your smallest unit b, right? For example, if you want your smallest unit b to be 1 month, then you should like adjust your bin to be that. And maybe like if you want it to be 2 weeks, or maybe like 2 months, then you just have to like change it to be something like that. At least you don't want it to be like bigger than that, right? You just don't want your bin to be like 2 months. If you want to like see the change in 1 month, then you just can't see it really. Is that accurate? I don't know.
I was following, and then in the very last minute, I lost you.
Yeah. So I think if your bin size would be like 2 months, then you just can't see the change that happened in a month. So like, for example, in this example, you just want to see like how much like differences in like a 0.1 SES. So you just, when your bin is like 0.2, then you can see the difference in 0.1 changes.
I see. So sort of like, are you saying that in something like a spline analysis where you want to try and understand trend and the shape of the relationship, having a smaller bin is going to make it easier for you to see that relationship? Maybe it'll be nonlinear if it's smaller. Maybe it will be linear, but something to check by making the bin smaller.
Kinda. I just meant that like if you want to like see like your units of change is 1 month, then if your bin is set for 2 months, then you can't see that change.
Right. Okay.
Yeah.
Right.
Like that.
So the X unit of interest, if it's 1 month, then make the bin size as 1 month.
Yeah, at least. So like, yeah. It just like if it's a still smaller, then it's okay, right? It just doesn't like, if it's bigger, then it's a problem.
Yeah. So mostly it's a problem of having a bin size that's too big that can give you a false notion that there's a discontinuity or a different kind of relationship. The smaller the bins, you don't run into that problem. You just have to remember that the purposes of binning was to make the scatter plot easier to see. And so if you make it too small and you end up with too many dots, then maybe it's hard. But oftentimes with bin scatters, you don't run into that, however small your bin sizes are. But you might run into a problem where you have such small sample size in that bin that the pattern that you see in that bin can be misleading because it ends up creating noise. So I guess that's the problem of having a bin that's too small, where you don't have enough observations, and the mean value for that bin can be misleading. But and so you have, so anyway, there's no like a firm defined rule on what the perfect bin size is. You have to test out different ones, and you have to diagnose whether you have enough observations in each bin and whether the pattern is changing by bin size. And of course, you want your results to be robust to all kinds of different tests. So lab is pretty much shorter than last time. And so for whoever is ready, you can feel free to jump off. And with some time left, I can go over like, how do you know if LPM and logits give you something similar, which is sort of a question on the problem set. But I can do that like now, or we can take a break, or maybe nobody wants to hear it, in which case we can all just end it here, and that's totally fine too.
Could I just ask a quick clarifying question? I'm sorry, I was a bit sleepy at the start, so I'm not sure if I understood this correctly. So you create bins, and then after you create bins, you collapse one variable that you want to calculate the mean for each bin.
Yeah, and it can be like many variables. Let's say you have like 10 outcomes, then you can take the mean of 10 outcomes. So
you generate the bin based on whichever size you want, and then for each bin, you calculate either the mean or standard deviation or anything, the options that you showed us in the help option, and then we create those, for instance, mean for science for each bin. Yeah. With collapse. Yeah. And when we do that, the other data goes away, so we have to save it elsewhere. Yeah, so because when you collapse the data set changes. It's convenient to save it if you ever want to go back to it. You can also do something where, like, let's say like you don't want to create these temporary files, and there are actual temp files that you can create. I'm just calling it a temporary file, but there's a function for a temp file. And you call it something, and then you can get rid of it, but don't worry about that now. You can also say like preserve before you collapse. Run your graphs, and then say restore. And what it will do is, let's say I use this, I'll skip over this long section. I'm going to run my data from here to here. It's now going to preserve my data at line 67. It's going to run all of these things, collapse it, run these figures, and it's going to restore it. And so if I didn't restore it, if I didn't preserve and restore, you're going to end up with like 40 some rows. If you preserve and restore it, it'll come back to you. So it's going now, it's creating these figures. And now if I look at the data, it's all there. But this is like something else to get used to. So like you can cover it, but you can just like save the data or like reload it, rerun your steps to get back to your data. So, cool. Other questions on binning, scattering, spline? Okay. Thoughts on taking a break or just continuing? Okay. Okay.
Okay, so we're gonna go back to our student level data. And we will run the problem set 6 question on predicting high and externalizing with math scores, controlling for some stuff, right? How do you know if they're giving you similar enough information, right? As an analyst, right, you want to make sure like your preliminary analysis is giving you a good enough picture. And then like as you work harder on this, like you want to make sure that LPM is giving you something similar to logits, right? And maybe for your journal, you have to talk about it in terms of like logits, but maybe you want to like push it off until later. But in order for you to like continue to like work on your analysis and you want to use LPM because it's convenient, you want to know that it's giving you similar enough information, or you want to make the case that it's similar enough, right? So you see this in a lot of papers where an author will say, I run it on LPM, I run it on logits, here are both results. They're similar, or like in the appendix is the logit. And in LPM, it will give you this kind of result. And logit and LPM were very, very similar. Right. So if you're writing for the econ journal, you might do that and push logits to the appendix. But more or less, there are some cases in which LPM and logits are not compatible, like they don't give you the same thing. But how would you know? How would you know that preliminarily it's good enough, that LPM is good enough? Thoughts?
I'm not 100% sure I understand what you're asking, but I thought we can just compare our coefficients from LPM to a logit coefficient that's converted using margins to predicted probability and compare it like that.
Yeah. That's like the probably the best way, right? Like you run logits, you take the mean value, at the mean value, holding things at the grand mean. What's the marginal effect of ZMath1? And then you have to make it like a judgment call. This is LPM. Negative 0.037. And then this is the marginal effect. Negative 0.039, maybe 0.40. Right? That's this, right? This, and you have to just make a judgment call like, it's similar enough, and I'll work with it, and I'll add this later, right? What's another way to see if if these two things are similar? That's definitely like the one obvious way, which you guys have already done. Another way.
I just had something in mind that maybe we can like consider 2 points, then like see what's their odds ratio, and also like compare them, like how much increase it would require in like LPM, and then how much increase would it require in logits, something like that.
So if we run LPM first, right, this is the result we got last time. And then we'll ask logit to give us an odds ratio. And you would compare these two numbers. Is that?
Yeah, maybe like I would say maybe like try to find what would be the like odds ratio increase when we like change from 20% to 80%, something like that, and then compare it to LPM model. So I just like I calculate the odds on 20%, then calculate the odds on 80%, find the odds ratio, then divide it by this coefficient. It would give me how much increase I would need in ZMath1, right?
So let me make sure I've understood. You're saying get the odds ratio at one value of X, get another odds ratio at another value of x, get the difference in the odds ratios. Is that what you mean? And
Yeah,
then,
yeah, yeah.
and then are you hoping it'll give you something
Log
like
odds.
this?
I think it would be log odds, right?
Log.
Anyway, yeah, here it is odds ratio. Then yeah, but just like if it was logits on its own, it would be log odds. But here you just add the OR. So
Yeah, I don't know. I don't know if I would ever use the odds ratio to compare it with the LPM. It's very hard, right? Like, I mean, you can compute multiple numbers, but I don't
yeah,
know that if I can get something that tells me it's similar enough to LPM.
so it would like you can compare the delta x if it just makes sense. You could like compare the increase in ZMath 1 in 2 cases.
So if I take the LPM, this is assuming that the slope is the same at all points of x. So the difference in slopes between 2 points is going to give you 0 because the slope is the same. And the odds ratio is the same across all values of x, because it's telling you in reference to before, incrementing x by 1.
Yeah, it just tells me if like the slope of connecting 2 points in logits, is it the same as the slope in LPM?
Oh, like, so okay, so take logits and not odds ratio now, and then take this difference, the change in the log odds, right? This change in the log odds is the same across all values of x. And so it doesn't give you the difference in slope, right? The linear slopes are different, but the change in the log odds is identical across the x, because it's all sort of log transformed. So, but also it's like really hard to like, that's a lot of work, right? Like compared to like taking the shortcut. But there's another way which we've sort of seen before on like how do you check whether your logits results and your LPM results are going to give you more or less similar results or maybe different results.
We can run a test, maybe?
What test?
I don't know. I was hoping you
Yeah.
could help on that.
No, sorry. There's no formal test, but you can predict y hats with logit, right? And then you can predict y hat with LPM. And then you can take a scatter of the two to see if they're giving you the same prediction for every person. And where is that scatter? And you'll get something like this that tells you it's pretty similar. It's pretty similar. You can add a line. Function y equals x. It tells you like most of this line, right? Tells you that they are more or less identical, except when you get to low values of x. So this is where, if for your descriptive paper, you wanted to interpret people who have low values of x and what their probability would be, right? Because you can choose what the marginal probability is, or a subgroup of your population that was down here. Or maybe your y range wasn't like super like broad from 0 to 1, right? From 0% to 100%. And it was really, the variance was happening between 0 and 20%, or 0 and 10%, or from 80 and 90%, which happens to be the case for like attendance, right? Or like the probability of absence or whatever, the proportion of time spent at school, where there's not a lot of variance, in which case using LPM could be bad, right? For the range that you care about. But these are two ways where you can kind of visually check. There's no like formal statistical tests, not that I'm aware of. But these are like two things that you might want to check, which isn't hard. Like make sure you run LPM, run logits, get the marginal effects, make sure they're giving you a similar story, plot out y-hats, and make sure they look more or less similar. Sometimes they'll deviate more and further here as you go towards the edge. And then feel sort of comfortable working with LPM and then bring in logits later. But of course, there are people who love logits, so I no need for this whatsoever. So that's it for today's lab. But I will stick around to answer whatever questions and hopefully fix the scatter problem that Amin pointed out. But I will do that on my own time. All right. Cool. All right.
Can I ask you a question about the exam?
Yeah.
About one question that Greg left out of the score. Do you know what it is?
Yeah. So Greg and I went back and forth a lot on this. I told him you have to put in margins dy dx or people are going to get confused. And if I were a student, I would give you two answers. Be like, if you meant this, then the interpretation is this. If you didn't mean this, then the interpretation is this. And then we decided on just changing the words into marginal effects instead of marginal probability, which sort of implies when you're saying marginal effect, it's the dy dx option. Marginal probability is the result you get when you just run margins. But because so many people had that confusion, it's like, all right, bad choice. We're just going to get rid of it. That's sort of the backstory.
Can you say
Yeah,
that
because
one more time? So you said the marginal effects is actually dy dx?
Yeah. Marginal effect is dy dx. And sort of like, I don't know if people use the word marginal probability, but that's what it would be for just the margins result. And there's a part of me that was hoping, like, if you had noticed that the graduation rate, right, the predicted probability, if you understood it to be just margins and not margins dy dx, it was like 8%. Like, that's a very low percent. And people should have been really like freaked out about their answer. Like, graduation rates are not that low, right? And so maybe that's sort of what pushed some people to figure out that it was the dy dx option, and they wrote about that. For others, they didn't, and so.
I freaked out because of the like so low value, but I freaked out and read it like several times and was like deleting stuff from my answers because it felt so wrong to talk about it, but I didn't notice that. No.
Yeah. Like another way to sort of check your internal consistency was marginal probability and LPM should not give you the same result. Only dy dx should give you a similar result to LPM. But I think the trouble with the exam was the LPM results were a little bit different, like substantially different from the LPM results, that it could sort of throw you off. But in terms of proportion, right, if the margins results that Greg was pointing to was like dy dx, your skeptical instinct, let's say you were a professor and a student came back to you and said, okay, the dy dx, like the marginal probability of graduating from high school is 8 percentage points, it's like an alarm bell should have gone off in your head. Like, he wasn't using the right option or she wasn't using the right option. But of course, that's not part of the exam, right? It's just like wishful thinking that it would be clear. Anyways,
yeah,
so
because that I mean I expected that to happen, that there is like something that we don't know, we can map it to the codes.
yeah.
And just like I asked you 2 weeks ago, that we at least be like clear.
Yeah.
Like see what he's asking from us, but just it still wasn't.
Yeah. Yeah. Well, so I guess some stress, no like harm in terms of grade. But it's how it's been dealt with. But that's the backdrop. Okay. Other questions on the problem set, the lab materials, anything about the course, the paper? I should note, I'm going to send out an email for people who want to use the Eccles K for their final paper. And if you want like the full data set, I'll make that available so that you can load it into your Stata and just browse around for whatever you want. Keep in mind that it has something like 20-something thousand variables. And so depending on your Stata package, it will not load in to your Stata. It's too big. I think if you're using the ones that's provided by school, then you can access it. I think it has the more expensive version of Stata. Another approach will be that if you can pick out the variables that you want, then I can add it to the class data set. But what I will not do is like take topics, like give me all the variables on social emotional. Like I'm not gonna look for all of that for you, but you can look them up online. I'll also provide a code book or like a descriptive output, so you can like pick out the variable names. If you wanted to work off of the new Eccles K, so the Eccles K that we're using for the class data set, which matches the Fry and Levitt paper that gets used often for our lecture. That one is looking at it birth, I think the cohort from 1998 or maybe older, and then a new cohort of Eccles K came along. They fixed some of the problems with the old Eccles K. So if you wanted to use the new one, I'll make that available too. I'll like send out a link or something. You don't have to work on the Eccles K, but that's the other piece. I think because next week there's no problem set, I'm debating whether it's useful to do an optional. I mean, the labs are already optional. No one has to come, right? Whether to do like a lab on like creating tables and figures that like, like the bonus stuff that you didn't do before. Like I might do them. I don't know if people want to see them done. Okay. But if there's enough interest, I'll cover those. All right. Cool. Questions? Cool. So I will end it here. Stop the recording.